Hello. Today, this video will be about the theorems to simplify algebraic logical expressions. The following will be the teammates which contributed to this video. Alright, for the first identity, the Boolean Additive Identities. The first two identities involve addition, whereby, as we can see, a plus 0 equals to a. This is because when 0 is added to any value, it doesn't change the original value. Whereas, when 1 is ORed to any variable, the answer is always 1, which proves the second identity. Next will be the third identity. This identity proves that any variable ORed with itself does not change the value. Next, the fourth identity can be proven when you assume that a is 0 and a is 1. The answer for both the assumptions will always be 1. Next, we will follow up with the Boolean Multiplicative Identities. The first identity and the second identity can be proven by simple multiplication, whereby 0 multiplied by anything will become 0, and the product of a variable and 1 is always the value of the variable. Next will be third and fourth identity. These two identities can be proven by assuming that a is 1 or a is 0. This will be the same as proving the third and fourth identity of the additive identities.
Now we will move on to the commutative law, associative law, and distributive law. The commutative law states that reversing the order will not change the truth of the expression. This means that A or B is equivalent to B or A, and similarly A and B is equivalent to B and A. The associative law states that groups of variables can be associated with parentheses without altering the truth of the equations. For example, A ORed with B or C in parentheses is equal to A or B in parentheses ORed with C. In a similar example, A ANDed with B and C in parentheses is equivalent to A and B in parentheses ANDed with C. The distributive law states that a Boolean expression formed by the product of a sum can be expanded. For example, A ANDed with B or C is equivalent to A and B or A and C. Now we move on to the Boolean rules for simplification. Rule 1 states that A or A and B is equal to A. To prove this, first we factorize A out of the equation and we will get A and 1 or B. And we know that 1 or B is equal to 1. So we end up with A and 1, which is equivalent to A. The next rule states that A or A naught and B is equal to A or B. To prove this, we have to apply the previous rule to expand the term. By expanding it, we get A or A and B or A naught and B. Then we factorize B from the second and third term, which gives us A or A naught in parentheses, which we know is equal to 1. So we get A or B and 1, which is equal to A or B.
Now it's my time to explain the meaning of DeMorgan's theorem. It's something that inverts the output of any gate results in the same function as the opposite type of gate with inverted inputs. For example, not A and B is always equal to not A or not B. Or similar to NOR gate, not A or B is equal to not A and not B. I'll show you how to use this DeMorgan's theorem in the correct method. For example, taking not A and B or C and D. After breaking the bar in the middle, you equal to not A and B and not C and D. Next, I will break both bar in the middle and it's equal to not A or not B in parentheses and not C or not D. And last, you simplify to not A and not C, or not A and not D, or not B and not C, or not B and not D. Next, I will show you what is the incorrect method for using this theorem. After breaking the bar in the middle is equal to not A and not B and not C and not D without any parentheses, it will lead to the answer not A or not B and not C or not D. This shows that it's important to maintain the grouping implied by the complementation bars. Next, I'll give you an extra examples. You can pause the video and give it a try. I will show you the solution in a second. And here is the working for this. This does not require any explanation because if you have been paying attention to this video, you understand this. Last but not the least, I will summarize the theorem to simplify algebraic expression. For basic identities, we will divide to additive and multiplicative. For additive, you can see here, but for the multiplicative, you can see over here. You can just memorize it. Next, I will show the algebraic properties. For the additive part, multiplicative, and the combination of both additive and multiplicative. And here is the Boolean rules for simplifying all the algebraic expressions. So, for the conclusion, we can simplify every single logical expression using those theorems. Second, we will be more proficiency in handling the input provided by the computer. And lastly, solving, analyzing, and designing a circuit is become more easier by using those theorems. Thank you for watching this video.